In our previous lecture, we were talking about the energy aspect of chemical reactions and how we could use that quantitatively in stoichiometric calculations. We hadn't looked at the actual quantitative part, but we did talk a little bit about the qualitative part. And we identified, first of all, reactions as either endothermic or exothermic, depending upon whether energy is absorbed or given off by a chemical process. An endothermic reaction is one in which energy is absorbed or taken on, as we can see from this first equation here. And endothermic reactions frequently involve decomposing or taking apart chemical compounds. Or a phase change, for instance, if we were talking about changing water from liquid water to gaseous water, that particular phase change is an endothermic process. Energy has to be put in to change it from the liquid to the gas. The other example we have here is then an exothermic reaction in which energy then is released. Exo or exit, and thermal meaning heat energy. So heat energy being given off. We also discussed briefly the units that are involved in talking about energy, the three that we may most frequently encounter: the joule, the calorie with a little c, and the calorie with a capital C. Actually, the calorie with the small c is the actual defined quantity, the amount of heat needed to change 1 gram of water 1 Celsius degree. And the calorie with the uppercase C is actually the food calorie, which really is equivalent to 1,000 of the others. So this one is actually 1 kilocalorie by definition, 1,000 of the regular calories. We just mentioned briefly in passing the British thermal unit, and I mentioned that only again to identify or relate energy relative to things like furnaces and air conditioners and things like that. That's not a unit that we'll use, and so we're not going to concern ourselves any further with that. Actually, the joule is the one that we're going to be concentrating on, and actually, in most cases, because the joule is such a small unit of energy, we're really going to be talking primarily about the kilojoule in most chemical reactions. Now, one equation that we can look at here on a commercial basis is the production of quicklime, as it's referred to, which is, as you can see from the chemical equation here, an endothermic process. We start with calcium carbonate, solid. Locally, that's called limestone. When you hear the term limestone, we're talking about calcium carbonate as an ore. And if we take calcium carbonate and heat it up, adding 178 kilojoules of energy per mole of calcium carbonate, we can decompose it into calcium oxide solid and carbon dioxide gas. Calcium oxide solid is what is referred to as quicklime. Normal lime is the hydrated form and is actually the form of CaOH2, or it's called calcium hydroxide or lime, and this calcium oxide is referred to as quicklime. Now, the reason that I particularly picked this one out to use as another example of endothermic and actual quantitative value involved here, not just energy as we had previously, is that we happen to live in an area that this is a very important commercial production. If you were to travel down Lone Pine street here in Springfield heading south as though you were going to go out of Springfield, you would probably drive by a plant that looks something like this. It is along down in kind of the valley area just to the south and east part of Springfield. And this is Oak Grove Lime Company. And the Oak Grove Lime Company is one of the major producers of quicklime in the United States. A very, very large manufacturing plant down there. You'll find a lot of white powder around, and the white powder is some of the calcium oxide that does escape in the processing. But this particular one, the source of the limestone or calcium carbonate, if you drive south on Glenstone, just before you were to exit Springfield, and you look again to the east, to your left, you'll probably notice a giant pit area. And if you were to go over closer to the edge and look, you'll see that there are actually trucks and that hauling material out of there. That is a major limestone quarry, which is used then to dig up the calcium carbonate, which is then transported to the Oak Grove plant, where it is processed by heating, then at high temperatures to calcium oxide, and shipped throughout the United States. So one of the practical applications of endothermic process on a commercial basis we see right here in Springfield. Let's take a look then at a couple of quantitative stoichiometric calculations involving then energy. The first reaction we have here is the reaction of acetylene with, looks like I cut off just a little bit of some things here, so we may need to recheck our balance on this one. Some acetylene, C2H2, a hydrocarbon, with oxygen to produce carbon dioxide and water. And this is an exothermic reaction. So notice that we release 1,080 kilojoules of energy in the process. And let's see, I think here that we have 4 carbons, and so the balance over here, I ended up punching a hole through the 4, I guess. It's 4 carbon dioxide, so in case we make a calculation involving CO2, we have the correct balance there. The first question we're going to ask is, if we were to react a certain amount of the acetylene, 0.866 grams, how many kilojoules of energy would we in fact produce? Now we notice that we have a stoichiometric relationship between energy and moles, just like we have a stoichiometric relationship between moles and moles. So we can use the balanced equation then, and again the ratio from the balanced equation, to proceed in solving the problem. If we look at the equation, it tells us what? It says 2 moles of acetylene, if we were to react it, would release 1,080 kilojoules of energy. Or 1 mole of acetylene would release 540 kilojoules of energy. That ratio of 2 moles to 1,080 kilojoules must be maintained no matter how much or how little then acetylene we react. Well, setting up the problem then, and the first step of stoichiometric problems in almost every case that we have done, the first step is to change to moles of known. I mean, that's always our first step. If it's already given in moles, we don't have to do anything. But this case, the known material is given to us in grams, and we must convert that to moles. So we'll set this one up in a continuous fashion. As I said, again, you can take it apart and do it in pieces if you prefer, but I'm going to go ahead and just put it all into one equation. So we're asked to calculate the number of kilojoules, and we're starting with 0.866 grams of C2H2. And As I say, we need to change that now to moles. So multiplied by 1 mole of C2H2 per number of grams. Carbon 12.01, again using our periodic chart of the table at the back of the text. So 2 times that would be 24.02, and then 2 hydrogens, each one 1.01, so that would be 2.02, and so we would have 26.04 grams for the formula mass for C2H2. Notice now that the unit's grams, and we're now at moles of the known substance. Now we look to our equation, and we can see a mole to energy relationship. And so we can use that now as our second conversion factor. We're going to multiply by 1,080 kilojoules of energy per 2 moles of C2H2. That is, again, the stoichiometric part of the chemical equation. Instead of being between a reactant and a product, or 2 reactants as we had previously, this time we're doing it in terms of a reactant and the energy involved. Notice that at this point we have kilojoules. We were asked for kilojoules. We should have the problem then properly set up, and we can go on and make our mathematical calculation. So plugging in our numbers here quickly, we have 0.866 divided by 26.04 and multiplied by 540. I just did that part in my head there, and we have a final answer of then 17.95. So 3 significant figures. We would need to write the answer 18.0 kilojoules of energy. Now, does our answer make sense? That's always a good thing to ask ourselves. Did that seem like a reasonable number? Well, if we just think about this for a second, if we reacted 26 grams of this, that would be 1 mole of it, we should have gotten 540 kilojoules of energy. So if we were to react, let's say, about 1 gram, or 1/25th then of that amount, we should have something around 20 kilojoules of energy. And our answer is quite close to the 20 kilojoules, so we see that just from an estimation, our answer does make sense. Any question on any step involved in that particular one? All right, let's look at one more example based on this same equation here. This time the question is, how many grams of carbon dioxide would be produced if 312 kilojoules of energy had been released? Now again, we would know that 4 moles of carbon dioxide would be produced if 1,080 kilojoules of energy. So we have an energy-mole relationship that we can use. And so we're setting up the problem then. Grams of carbon dioxide is our unknown. And this time our measured quantity is 312 kilojoules. Now somehow I need to get rid of the kilojoules, and again, going back to our equation up there, we can relate kilojoules to moles. And so we can now say there are 4 moles of carbon dioxide produced for each 1,080 kilojoules of energy. Our kilojoules have now canceled, and we're at moles of carbon dioxide. Now, we didn't ask for moles of carbon dioxide, however. We asked for grams of carbon dioxide, and of course that we can do because now we know we can bring in our relationship of mass to mole that we talked about already in Chapter 2 as well as here. And so then we're going to now multiply by the number of grams of carbon dioxide in 1 mole of carbon dioxide. Now, when you cancel the units, make sure that you don't accidentally cancel the number, too. I mean, we don't want to cancel this 4 out. We're just canceling out the units. Well, 2 times 16 for the oxygen would be 32, plus the 12 for the carbon, and 12.01, and so we would end up with a mass of 44.01 grams of carbon dioxide per 1 mole. Notice that we now have grams on both sides. Again, the problem is properly set up. Well, let's see what we get quickly for an answer here. We have 312 divided by 1080 and multiplied by 44.01, and we have an answer of 12.7 grams of CO2 would be produced in releasing then the 312 kilojoules of energy. Any question on that one? Yes, a question back there.
Why when you brought down the 4 moles of CO2, why was that not really in grams? Is it because it's on the right-hand side of the calculator?
The question was, if I understand it, when I brought down this 4 here, why was it expressed as 4 moles and not grams? Is that correct?
Yes.
All right. The answer to that is that our equations are always in terms of moles. When we read this equation, it's 5 moles plus 2 moles gives 4 moles plus 2 moles. Because not everything weighs the same. We're not talking about 5 grams of this and 2 grams of this. It's 5 moles of this and 2 moles of this. Chemical equation is always in units of moles. Okay? Other question, yes?
If we're using the kilojoules, don't we also have to use kilomoles?
No, we do. No, we do not need to. That's good, very good question, because in a previous problem we looked at, we did look at how we could stoichiometrically use kilograms and then go to kilomoles and not have to change back to grams. No, in this particular case, the energy is given to us in kilojoules, and all we are saying is 1 mole is that number of kilojoules, okay? So we don't need to make that same type of conversion we did before. And we had one other question.
Yeah, when you brought down to 4, how are you delivering that down to the same side as the 1,000?
The question was, when I brought down the 4 moles of the CO2 here, how could I do that if it's on the same side as the 1080 kilojoules? In stoichiometric problems, let me emphasize, we can work any 2 things in the problem. It doesn't make any difference. It doesn't have to be a reactant and a product. We can look at 2 products. How much of one product will we get if we get a certain amount of another product? How much of a product will we get if we get a certain amount of energy? How much reactant will it take to get a certain amount of product? If we want a certain amount of product, how much reactant do we need? Or if we start with one reactant, how much of the other reactant do we need? So any 2 things can be related from the stoichiometric problem. Okay, so they can both be on the same side, no problem at all. All right, any other questions on that? Yes, question over here.
Did you multiply by 4?
Oh, well now, you know, I think maybe I didn't. So somebody is wide awake this morning. The question was, did I actually multiply by the 4 here, and is this the correct answer? And now that mentally I think about it, I think I did this and this and that, and I don't think that I did multiply by the 4. So our correct answer, so we need to still multiply by 4, and that's good. Keep me on my toes. 50.9 grams would be the correct answer, not 12.7. All right, any other questions on that problem? Well, let's go on and take a look at one more here. This one is a chemical equation that we're quite dependent upon as animals. And this particular chemical process, which you see, which is endothermic, is the combination of carbon dioxide and water to produce C6H12O6, which is what we call a carbohydrate. This is photosynthesis occurring. So photosynthesis, of course, is how nature stores a lot of the solar energy in a chemical form that we can use it as human beings, as animals. We are dependent upon then our source of carbohydrates from plants or from animals that have previously eaten the plants, but our carbohydrate source is dependent upon photosynthesis. The ability of plants to take carbon dioxide and water in the presence of some other chemicals that we'll talk about in Chapter 14 in biochemistry, and put these together to make then carbohydrates, which we use, of course, as a food source. In addition to that, notice one other part of this reaction, and that is the production of another product, oxygen. Well, that's also pretty important because we have to breathe oxygen. And so plants do three things. Plants remove carbon dioxide from the air so that we don't get too much CO2 in the air in the first place. Store the energy as carbohydrates, which we can use, and secondly, replace oxygen back into the atmosphere so we maintain the oxygen in the atmosphere at about 18%. So plants are very, very important as far as life on Earth is concerned in these cycles that involve then several life-giving or life-taking processes in the overall scheme. Notice, as I say, it's exothermic. That's the amount of energy, that's the amount of solar energy absorbed as heat energy by the plant to carry out the photosynthesis process. Question this time is, how many grams of this carbohydrate, C6H12O6, would be formed if a plant absorbed 586 kilojoules of energy? And so our unknown this time will be then the grams of the carbohydrate. So grams of C6H12O6. And our measured quantity that we're starting with is 586 kilojoules. Our first relationship then must be to somehow relate energy to the carbohydrate. And of course we can do that then from our balanced equation, in which we see 1 mole of the carbohydrate uses that number of kilojoules of energy to produce it. So multiplied by 1 mole of C6H12O6 per 2,803 kilojoules of energy. So now we're at moles of the unknown substance, and of course our final step then will be to convert to grams. So now we need to calculate the number of grams of C6H12O6 that we have per 1 mole, so that those units cancel and we'll be left with grams. Well, let's see. We're going to have 6 carbons, so 6 times 12.01 would give us 72.06. We're going to have 12 hydrogens, 12 times 1.01, so that would be 12.12. And 6 oxygens, 6 times 16, 96 grams for the oxygen. And let's see, we'll have 0.18, 0, 89, 180.18 grams of carbohydrate per 1 mole. And so our final step then would be to convert to the grams, multiplying through now. The units check, so we're comfortable we have it set up right. 586 divided by 2803 multiplied by 180.18. And in this case, we're again limited to 3 significant figures based on the measured energy quantity. We could have had 5 here or 4 here, but only 3 based on the energy input. And so our final answer is then 37.9 grams of C6H12O6 would be produced. Okay? One last part on this one then, relating to the same equation. This time we're going to ask the question, how many kilojoules of energy would be absorbed by a plant if it were going to react, if it were going to use up 1,000 10 to the third kilograms, 1,000 kilograms. That's not 1 kilogram now, we're talking about 1,000 kilograms. This is referred to, 1,000 kilograms is referred to as a metric ton. A metric ton. A ton, English-wise, is 2,000 pounds. A metric ton would be then 1,000 kilograms, which is actually around 2,220 pounds. So a metric ton is about 10% larger than a normal English ton as we describe it. How many kilojoules of energy are going to be absorbed? Now, a moment ago we had a question about did we not need to use kilomoles because we were using kilojoules, and I said that we didn't need to do that because we were using kilograms. Notice this time now we are talking about kilograms, and so we do have two pathways. We can convert from kilograms to grams and solve it that way, or we can just go ahead and put it in terms of kilograms and kilomoles. So we'll look at it in terms of units using the kilo this time. All right? So we're going to say kilojoules of energy. And the number of kilojoules of energy is going to be equal to 1 times 10 to the third kilograms of carbon dioxide. And the first thing that we want to do then is to convert that to moles, or in this case, we're going to convert it to kilomoles. So 1 kilomole, 1,000 moles of carbon dioxide, would weigh 44.01 kilograms. Now, I recalled that number from our previous example problem. We worked the molar mass of the carbon dioxide, 44.01. So that's where that came from. Notice now that we have that canceled out. Multiplied by. All right, in this particular case then, now we're looking for the CO2 relationship and the energy relationship. And we want the CO2 on the bottom, obviously. So we're going to say kilomole of CO2. All right. Now, if we do that, then up here, of course, we're going to have to bring in a 10 to the third factor as well. If we're going to multiply this by 1,000, we must multiply that by 1,000 as well. And so we would have 2,803 times 10 to the third, that's where I'm multiplying by the 1,000 to make up for this kilomoles, then kilojoules. It was already 2,803 kilojoules for 6 moles. But if it's 6 kilomoles of CO2, which is 1,000 times as much, it would be 1,000 times as much energy. And then we notice that the kilomoles will cancel, and we're ready then to calculate the amount of kilojoules of energy. That's all we have left for units. Yes, I have a question in back. The question is, where is the 6? And that is a very good question, because apparently I lost the 6. So we do need 6 kilomoles of carbon dioxide per 44 kilograms. Okay, very good. Yes, question again.
Can you put the 6 on top instead of putting it underneath the kilojoules?
The question was, I put the 6 kilomoles of CO2, okay, per, oh, no, 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 no. Yes, 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 yes. No, 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 no. Yes, yes, yes. Okay, back to okay. The question was not this one. And the question, so let me go ahead and redo this. This is 1 kilomole of CO2. The 6, I forgot, was here. All right. So hopefully now, after all of that, I have finally got it set up correctly so that we now have 6 kilomoles of CO2 per 2,803 times 10 to the third kilojoules of energy. All right, so we do need to keep in mind, keep track of our stoichiometric relationship better than I did. All right, now we could work the problem out and obtain then the final answer. So we would have 2803 divided by 6 and divided by 44.01, and we get an answer of 110.6 times 10 to the 6th. I didn't do that, I just doing this part mentally. 10 to the third times 10 to the third kilojoules, or 1.06 times 10 to the 7 kilojoules of energy, writing it in scientific notation. Question over here.
Yeah, I'm a little confused on endothermic and exothermic. If I heard you right, you said that this was an exothermic?
No, no, this is an endothermic.
Okay, that's what I thought.
Yeah, energy is being put in. Okay, I might have, I hope I didn't, but it is definitely an endothermic process. I have a question back there.
On the 44.01 kilogram of CO2, shouldn't that be balanced out too with the times 10 to the third, or is that just?
The question was, should not the 44.01 also be 10 to the third? The answer is no, because we have, it's 1 mole per 44.01 grams. It's 1 kilomole per 44.01 kilograms. So I have actually multiplied both the top and the bottom by the 1,000 when we put the kilo in. All right? All right, any other questions on that one? Yes? We could have, in this particular case, measured quantity is, well, that would depend upon what we're calling this as a measured quantity. That would be 1,000, which could be considered 3 significant figures. Or we could count it, not count that one, and then if we go to those two, it would be 4 significant figures. So 4 or 3. Okay. All right. Because this one isn't stated in any specific way, so we don't know if it's 1.00 kilograms, or I mean 1.00 times 10 to the third kilograms. That would be, of course, a 3 significant figures, or if we're talking about an exact 1,000. And as a measured quantity, there would be some uncertainty somewhere. So, any other questions on that one? All right. To wrap the chapter up, I thought we would just look at one more example problem here and work 4 different questions into the problem. Just to kind of review a little bit of what we've talked about stoichiometry, other than for the energy which we just finished up. We have a chemical reaction here. This is one that we have looked at before. This is propane reacting with oxygen, CO2, and water, and we would get energy. It's an exothermic process. We're starting with 15 grams of the propane and 37.5 grams of the oxygen. And the first question we're going to ask is, how many grams of water would we produce? So this is going to be our first question. How many grams of water will we be able to produce in this reaction? This takes us to the question of limiting reactant once again. The amount of product that we can produce, of course, is going to be limited by whichever one of these is used up first. And as I said, if we're starting with 2 reactants and a measured quantity for each one, probably the easiest way to set it up is set it up as 2 calculations, one asking the question, how many grams of water would I produce based on the 15 grams of propane? And then I would ask, secondly, how many grams of water am I going to produce based on the grams of oxygen that I had? And the lesser number is then going to be the number of grams that we have actually been able to produce. Now, because we're going to go from grams to grams, of course, this usually takes a little bit more space, so we'll just slide that up a little bit, and I'll try to work right down here below it. And so I'm going to ask the question now, grams of water. And the first time through, I'm going to be looking based on the C3H8. So we're going to start with 15.0 grams of C3H8. Step number 1, of course, is to convert to mole. 1 mole of C3H8 per number of grams. So that unit will cancel. Well, we'll have 3 times 12.01, that'd be 36.03, plus 8.08, that would be 44.11. So we've now converted to moles of propane. Multiplied by 4 moles of water per 1 mole of propane. And that, of course, comes from our stoichiometric relationship, which is up a little bit too high to see there, our stoichiometric relationship of 1 mole to 4 moles on the water. And finally then, to convert that to mass of water, multiplied by 18.02 grams of water per 1 mole of water. And we see now we're at the point of having grams on both sides, so the problem is set up correctly. So running through the math quickly here, we have 15 divided by 44.11 multiplied by 4 and then multiplied by 18.02. And we get an answer for the first calculation of 24.5 grams of water. Now we're going to do the same thing, except this time we're going to look at oxygen and water in our calculation. And so we're going to set everything up exactly the same again. Grams of water based on oxygen. 37.5 grams of oxygen multiplied by 1 mole of oxygen per 32.0 grams of oxygen, 2 times 16, actually 32.00, multiplied by 4 moles of oxygen per 5 moles, 4 moles of water per 5 moles of oxygen. That again goes back to our stoichiometric relationship from the equation. And finally, multiplied by 18.02 grams of water per 1 mole of water. And our units now have all canceled except 4 grams of water. So working through that one quickly, we have 37.5 divided by 32 multiplied by 4 divided by 5 and multiplied by 18.02. And we get 16.9 grams of water. So the first question was, how many grams of water could we produce? And the answer is 16.9 grams. That is the lesser amount. Question? The question was, where did the 18.02? All right, that's the mass. At this point, before we put in this step here, we were at moles of water. But we weren't asking for moles of water, we were asking for grams of water, so we had to put in our molar mass ratio to get to grams. Now, we've answered the first question, and we have now answered the second question. The limiting reactant is, in fact, the oxygen. Even though it's in the greater amount, 37.5 grams, as we see in the problem, it is actually the one that will be used up first, and that's when, of course, the reaction will stop. Now, question number 3. How many grams of excess reactant do we have? The propane is in excess. We didn't use all of it up. And so the question is, how many grams of propane do we have left? We started with 15. How many are unreacted? What we're going to have to calculate then is how many grams of propane reacted. If we know how many reacted and we know how many we started with, we can, of course, determine the amount that was used up. So we're going to say grams of C3H8 reacted. We know that all of the oxygen reacted. So that is our part that we're going to use as the starting amount, 37.5 grams of oxygen multiplied by 1 mole of oxygen per 32.00 grams of oxygen. And using our stoichiometric ratio multiplied by 1 mole of propane per 5 moles of oxygen from our equation, and then multiplied by the mass, and let's see, I think we calculated that a moment ago, 44.11 grams of C3H8 per 1 mole of C3H8. That would cancel out. And we can now calculate the number of grams of propane that reacted. So 37.5 divided by 32 divided by 5 and multiplied by 44.11. And we find that 10.3 grams of propane reacted. The question wasn't how much reacted, the question was how much propane did we have in excess. Well, the excess, of course, would be the difference between what we started with and what we reacted, and so the excess number of grams of propane would be 4.7 grams of propane in excess. Okay? The final question of the problem is, what is the percent yield? If we found that in actuality we produced 14.7 grams of water, then what is the percent yield of the reaction? Well, just a moment ago we calculated that we could produce, then from the reaction we could produce 16.9 grams. That was our amount that we were going to produce. And therefore that's the number that theoretically is the number of grams of water that we could produce. At that point, then all of the oxygen would have been used up. But what the question is saying, in actuality, not everything did react, and we actually only produced 14.7 grams. What is the percent yield? Well, we said the other day percent yield is equal to the grams actual divided by the grams theoretical times 10 to the second. This gives us then our overall percent yield. So in this particular problem then, we have 14.7 grams were actually produced. 16.9 grams theoretically could have been produced. Notice grams will cancel. Percent should be a unitless number. And so now if we take then 14.7 and divide by 16.9, we see that our reaction was 87.0% was the yield of the chemical reaction. Now, any questions on any step of that problem? Important on limiting reactant problems, first of all, that you solve for both, because you cannot look at the magnitude of the numbers. This one might look like that's in excess. In actuality, that one is the one that's the limiting reactant. So you cannot just look at the two numbers. You must make a calculation for whatever it is that it's asked about based on both. Then you can determine which is the limiting reactant to the problem. All right, any questions on any part of this information from Chapter 3 on stoichiometry? All right, as I indicated, then there is a problem set due tomorrow, so you'll need to be working on that. In our next lecture, we'll begin looking at solutions and solution chemistry and solution stoichiometry. So once again, we're going to be going back to this stoichiometric calculation. So Chapter 3 is important from the standpoint of getting a good, solid understanding of stoichiometric reactions. And we'll start that then in our next lecture.